What if a chemistry classroom felt less like memorization and more like a research lab? That's exactly what one Qatar teacher is making real. I'm EduBot, an AI designed to explore innovative teaching models. Today, I'm speaking with Ms. Fatima Al-Sharoki, a grade 12 chemistry teacher who brings computational thinking and digital simulations into her lessons. Ms. Fatima, how do you integrate computational thinking into the Qatar chemistry curriculum to deepen your students' scientific understanding?
Thank you, EduBot. In my classroom, chemistry is not only about memorizing formulas and reactions. It's about exploring systems, identifying patterns, and understanding how scientific processes work. Let me demonstrate how I integrate computational thinking into chemistry learning through 2 lesson designs aligned with Qatar Grade 12 chemistry curriculum. So, my first lesson is about how temperatures affect the rate of chemical reactions, a classic topic, but one students often struggle to visualize. Instead of just explaining it theoretically, I built a scratch simulation where students actually get to play with it. They drag a temperature slider and watch the particles on screen move faster, collide more. It just clicks for them in a way a textbook diagram never quite does. Now, to keep the lesson structured, I follow the 5 E's instructional model, and if you are not familiar with it, think of it as 5 stages that take a student from curiosity all the way to confident understanding. Engage, explore, explain, elaborate, and evaluate. We kick off with engage. Students look at something as simple as boiling water and ask themselves, what is temperature actually does to those molecules? Then comes explore. This is where simulation comes in. Students adjust the temperature themselves and observe what changes. In the explain phase, they connect what they saw, faster molecules or particles, to the actual chemistry concept, more frequent, effective collisions. Elaborate pushes them further. Can they link this to cooking, to industrial reactions? That's where it gets exciting. And finally, evaluate. Students explain what they observed using evidence from the simulation, not just from memory. What I love about this activity is that it also quietly builds computational thinking skills. Students break the system down: temperature, particle motions, collision rate, that's decomposition. They spot the pattern between heat and speed, pattern recognition. They zero in on temperature as the one key variable, that's abstraction. And by adjusting the slider step by step and analyzing what happens, they are participating algorithmic thinking. By the end, they are not just learning chemistry, they are thinking like a scientists. Now, building on the same idea, learning by seeing and doing, my second lesson takes on thermochemistry, specifically the difference between exothermic and endothermic. This is a topic where students often just memorize the definitions and move on. Exothermic release heat, endothermic absorb it. Fine, noted, forgotten by next week. So, instead, I use Sprite Lab from code.org to build an interactive simulation where students actually watch the energy move. In this simulation, a reaction happens and temperature either climbs or drop, and that's the moment where I ask them, why did it go up, why did it go down, and what does that tell you about what the reaction is doing with energy? Suddenly, enthalpy change isn't an abstract formula, it's something they just observed. And again, computational thinking is woven right through it. And by this point, in this lesson, students are actually starting to recognize the framework themselves. They use decomposition to separate out the pieces, the system, the surroundings, which direction the energy is flowing. Then pattern recognition kicks in. Temperatures goes up, heat was released, that's exothermic. Temperature drops, heat was absorbed, that's endothermic. Simple but powerful once they figure out, rather than being told it. Abstraction helped them to cut through the noise and focus on what really matters: energy transfer. And with algorithmic thinking, they build a mental checklist. Observe the temperature change, determine the direction of energy flow, classify the energy and reaction step by step every time. What I find really rewarding is that by lesson 2, students are not just applying computational thinking, they are starting to accept it as a part of how science works. And that really is the heart of it. When students are dragging sliders, watching the particles collide, and figuring out why the temperature drops, they are not passive anymore. They are investigating, questioning, testing ideas. The chemistry is there to discover, not just mine to deliver. To me, that's what happens when scientific knowledge, digital tools, and computational thinking comes together. Students don't just learn STEM, they are starting to think in it.
Analysis complete. These lesson designs demonstrate how technology, computational thinking, and scientific inquiry can transform chemistry education. By encouraging students to analyze systems, recognize patterns, and think logically, this approach supports the development of innovative learners. Such practices align with the goals of Qatar National Vision 2030, which emphasizes building a knowledge-based society driven by science, innovation, and advanced education. Students are not only learning chemistry, they are learning how to think like future scientists and innovators.